Fundamental counting principle and our understanding of probabilities of simple events allows us to summarize and say that the probability of two compound events, or events that are happening one after the other, is just a matter of our being able to multiply the probability of the first event and the probability of the second event for the compound probability. You'll notice that in the compound probability that we use the word then. We're imagining the situation where something is happening and then something else is happening. We are chaining the two of them together. So when we chain two probabilities together, the key is to multiply those probabilities together, not add them. Lots of people think that you're so used to when you put things together to add them, but that's not what's happening here. So let's take a look at this first example. We have 7 cards that are labeled with A, E, I, O, U, P, and C. You choose a card, replace the card, and choose another. We see the word then, meaning we're going to need 2 fractions, one for A and one for E. So the first time I reach in, my chance of getting an A is 1 out of 7. It is one of the 7 cards. My chance of getting an E is also 1 of 7. It's one of the 7 cards for a grand total of 49. This 49 represents the total number of combinations. This 1 represents how many of them are A and E. Now notice that's not the same thing as E then A. E then A would still be 1 out of 49. It's just a different one of the 49. How about an O then an O? Well, obviously still 1 out of 7, followed by a 1 out of 7 for 1 out of 49. Again, the 49, still the total number of combinations, and then that 1 is the OO combination. We refer to this scenario as an independent compound event. The removal of the first card did not have any impact on the second card. Why? Because I replaced the card in the deck. We call that with replacement. That's the putback. We took a card out, and then we put the card back in. Let's contrast that to a situation where we don't put the card back. We should expect some change in the probabilities. If I have these 7 cards, A, E, I, O, U, P, and C, I'm going to choose the card, hang on to it, then go back for another. Well, the first pull's still going to remain the same. But the second time I go in, if I'm still holding on to the A card, that A card's no longer in the deck anymore. E is still there. There's still 1 E in the deck, but there is not 7 cards in the deck anymore. There are only 6. Our total number of combinations drops to 42, but we still have a 1 in whatever chance of getting it. Hopefully you can see why this 7 dropped to 6. I held on to the A card. I didn't put it back. So my second probability needs to be a little bit different. Let's do it again with O. I still have a 1 out of 7, but now when I go back, I'm going to have 6 cards, but do I have the ability to get an O once I've removed it from the deck? Obviously not. And I run into this interesting situation where what previously worked as a combination, 1 out of 49, no longer works. One of the 7 combinations that I got rid of, so I dropped from 49 combinations down to 42 combinations. One of the 7 combinations that I got rid of was the OO combination because I was not able to get that card again. When you hang on to the item and don't replace it, we call that without replacement or a series of dependent events. In a dependent event, the first event changes the probabilities for the second. Something happened in the first step of the game that made the second step have a different probability.